Yes. All right. I think we're good. I'll get started. You can take care of that.
I'll fix this.
Okay. There we are. All right. Yes. So JRuby guys, back together finally. 5 years since we presented together at RubyConf. Really glad that we were able to get together. Here's some information from us. I'm co-founder of Hedius Enterprises, which I'll talk about in a second. And Tom is looking for work. Okay. So I mentioned Hedius Enterprises. Recently, the JRuby project lost its major sponsor, so we've both been looking for ways to keep the project going. I have started a company, Hedius Enterprises, to do commercial support for JRuby users. You can grab this QR code if you or anybody you know is interested in migrating to JRuby to get better scalability, or you've got a JRuby application that you would like some professional support for. We've got a wide range of options to help you with that. Along those same lines, we've got stickers, finally, a new reprint of JRuby stickers that have all the information about JRuby support on them. Please come up afterwards and grab a couple to bring back to your teams. So a little intro on JRuby. We're going to be talking mostly about JRuby internals here. But of course, JRuby is Ruby for the JVM, and the flip side, bringing the JVM to Ruby. All of the capabilities of the Java platform with good JIT compilers, amazing garbage collectors, parallel execution, and deploying across lots of systems. We've also got this giant ecosystem of Java libraries, Java tooling, really brings a whole large world to Ruby, and we also get to use Ruby in the environment that we're familiar with. The development experience is pretty much the same. You use the same command lines, all the same tools run. We have a very high level of compatibility. Give it a shot and come by the Hackfest tomorrow and we'll see if we can get some stuff running.
Okay, so we're going to do a very short roadmap update. Our current release of JRuby is JRuby 9.4. It's compatible with Ruby 3.1, so it's getting a little long in the tooth for compatibility. We just put out our last release last week, and the big statement is after we release our next version, JRuby 10, we're going to give approximately 1 year until we end of life this, but we've been pretty lax on this. If someone actually needs a little longer, we usually don't leave people hanging. The next big thing is JRuby 10. It's going to update and catch up to CRuby. And in fact, up until the point that we had lost our jobs, we were going to release this at the exact same time as CRuby. But we've only drifted it a couple of months, and we should be able to make it. And then we're out. We'll wait till we come back. Ooh, do we get any bonus time? So the big change is that we're going to stop supporting Java 8, and we're going to go up to the newest long-term support version of Java, which is Java 21. And Charlie's going to, oh, wait. No, I'm still going to go. So the good news with 10 is all the language features are completely supported. The only thing that we haven't done is there's still some core APIs that need updating. So it shows like maybe 450 errors between the two test suites, but there's a lot of duplication, and like one missing keyword might be 20 spec failures. So we're actually quite close to being done.
So there's 2 of those for some reason.
I'll do it a second time.
All right, so before we get into the internal details of JRuby, we'll do a quick little walkthrough of the how to get involved in the project. So working with JRuby, building it is very simple. The hardest part is probably just installing a JDK. Use whatever package manager you've got. Go and download one of the many distributions that are out there. They'll all work just fine. You clone our repository. You run the Maven command we've got built into the repository itself, and that's it. You have a completely working JRuby environment that you can do all of the same Ruby stuff that you would with regular CRuby, except it's now going to run on top of the JVM. Quick code base tour here. Most of the core of JRuby is in the core directory. There's mostly Java code, but also a little bit of Ruby for some of the implementation. The lib directory is where all the gems and standard libraries are. The test and spec directories are where we have all of our various test suites. We run a couple dozen different test suites to confirm JRuby works properly. And then the bin directory is where all the gem executables go, and that's where the JRuby launcher is. I mentioned the kind of the ratio of code in here. This actually has gone down over the years. It used to be around 400,000 lines of Java code. Now down a little less than 300,000 lines.
Maybe change the C port.
And we're pulling more code from Java into Ruby as we go on. It makes it a little easier for us to optimize, and it's a little bit better for maintainers, contributors from the Ruby community to help out. Try and continue here. So once you've got it up and going and you're able to build it and you've got the code, we recommend IntelliJ as the IDE that we use. It's what we use on a daily basis. But other editors and IDEs out there will work just fine as long as they've got support for a Java code base. There's plenty of JVM profiling and monitoring tools out there. I've done other talks on them that you can look up. We're not going to go into some of that here. But we can benefit from all of the tooling on the JVM without really any changes. You can run your Ruby application on the JVM and use the same tools that the Java folks are used to. All right, and I'll hand it back to Tom here.
Yeah, so now we're going to talk about some of the core pieces of our code base. We'll start with the parser. JRuby 10 actually has two parsers, the parser that we've been using for the last 20 years, and the new parser, which is Prism. It's an external open source project. And for the most part, if you want to contribute to this, we can ignore the parser part of this. But if you do want to work on parsers, go and contribute to Prism. The next big chunk is our internal representation. This is largely changing the tree that the parser generates into a sequence of instructions. The instructions are pretty obvious, like we have a call instruction for calling a method, define method. I'll let you guys figure that one out. But when we need to implement something like a if statement or a loop, we need some branches and jumps. So we add a few computer science-y instructions. And the operands are also fairly obvious: string, hash, array, local variable. We have a temporary variable that's new. So at the bottom here, we're calling 1 plus 2, and we're storing it to a temporary variable. Let's just go through a simple example where we go and look at a single node, and we're going to build instructions from it. So if we look at IR Builder, the thing that builds these instructions, the first thing we have to do is we have to get the global variable using get global variable for $_. We save it to a temp, and then we add a match instruction that binds that $_ variable to the regular expression from the tree. And so generally, we only have to change IR Builder when there's new language features, but sometimes we realize we're doing something inefficiently, and we figure out a better way of doing it. So there's some performance work. But IR is much bigger than just the builder. We have a bunch of compiler passes. We have 2 interpreters. And if you want to contribute to JRuby and you're interested in language implementations, this is a really fun spot to be.
All right, so I'll talk a little bit about where the IR goes from there. So here is the compiler pipeline of JRuby. We've got our Ruby code coming in on the left. That gets parsed and compiled internally to our intermediate representation, our instructions, very similar to the YARV instructions on the C Ruby VM. And then we interpret those for a while, and that's kind of as far as Ruby has gone since 1.9. Create a list of instructions, run the interpreter. But of course, in C Ruby and in JRuby, we want to go beyond that. We want to get rid of the interpreter overhead. So our next step then is to just take the Ruby intermediate representation and compile it into JVM bytecode as efficiently as we can. From there, we don't have to do any more work. We let the JVM take it. The JVM will interpret it and profile it, pass it off to its JIT compilers, and then over time iterate over it and get the best performance out of it. All we had to do was get the JVM bytecode in there for this Ruby code, and we get the benefit of all of those optimizations. So I'm going to walk through a little bit of the code that's involved in executing IR, and then how it feeds into the JIT compiler for JRuby. So every one of the literal types, float, fixed num, string, etc., has an operand type in our IR. This is the float operand, part of the implementation. We can see it up at the top here. It extends the immutable literal. Does that show up on there? Yes, there we go. Immutable literal, because this is an object that we will create once and then cache. We have a final double value here, not too surprising, a simple constructor. And then once we get to the interpreter will call into this, use this operand to determine how to create a float object, and then cache it for us so that we don't keep creating the same object. We also have this visit method, which is used for us to translate IR into other forms. We have a pretty printing dumper that will print it out on the console with color and formatting so you can see your IR. But for the purposes of this talk, we go into the JVM visitor, which turns IR into JVM bytecode. So IR visitor is the superclass. Here is just a snippet, a few of the different operands that you can implement. And then eventually we end up in the JVM version of that visitor. So we feed in our float operator, or our float operand. We grab the current JVM method that we're emitting. We get the compiler that emits values for it and tell it to push a float onto the stack. And most of JVM visitor looks like this, calls through these abstract interfaces because we have a few different ways to compile things. So for pushing a float in our value compiler, there are two different ways that we might emit that code. One is sort of normal JVM bytecode. We're going to cache this value, so we have a helper to cache that value permanently. We push our JRuby runtime onto the stack. That's this code here. LDC is pushing a constant, so we push the constant double value onto the JVM stack, and then we call new float to create the object. And then this cache permanently will save it for us and emit the right JVM bytecode to do it. We also use a feature on the JVM called invoke dynamic. It allows us to teach the JVM how to optimize Ruby code like it would Java without having to do any native code. And down at the bottom, it's much simpler here. We have have our double value, we load our current execution context, and then we just invoke dynamic, the float operation, and it passes in that double. I mentioned invoke dynamic here. So this is basically a JVM bytecode for doing any dynamic binding on the JVM. Instead of just doing one of the existing JVM operations, we give it a special object that says, here's how you optimize it. Here's how you turn this into fast code. So this has allowed us to teach the JVM how Ruby can optimize and get performance much closer to native Java and eventually native C code. So here is the bytecode we get out of this. The bytecode on top is the normal-ish JVM bytecode. Notice a get static and put static at the beginning and end. That's basically checking if we've created the object already. If not, we store it in a static location so that we don't have to recreate it every time. The invoke dynamic version is only two operations. This is the loading of our current execution context and then our invoke dynamic. And the magic of that, so up here we have our new float creation. The magic of the invoke dynamic is we tell the JVM, go to this class to get the way of compiling this instruction. If we look at our float object site, this is what goes to the JVM and says how to optimize a float construction. Again, we've got it's a lazy object we're going to create. We have our final double value in a simple constructor, and then we construct the new float, pass it back to the JVM, and it caches it like a constant. And interestingly, this is almost identical to the original operand that we had in IR. So we're basically making new instructions for the JVM that are simply a version of the interpreter instructions, but doing it in such a way that the JVM can optimize it like Java code. All right, so a little review before I move on here. Parser creates the abstract syntax tree. The IR compiler turns the AST into our instructions. We interpret those instructions for a while and learn a bit about them. Eventually, we take our JIT compiler and turn the interpreted instructions into JVM bytecode. And then the JVM takes off with it and continues to optimize it. But what about all of the other classes that we use, string and array and so on? So let's go into how JRuby implements the core classes of Ruby. So all the core classes like string, array, hash, and the numerics and such are generally in the org JRuby package, Ruby string, Ruby array, Ruby hash. Pretty easy to locate these. Compatibility in JRuby very closely follows CRuby. So you'll notice if you look at the code, the implementation of our core class methods and the implementation of JRuby are very similar. There's only so many ways that you can concatenate two strings or add two numbers. So the logic is often a line-by-line port of the C code from JRuby. Things that are different, we use Java features that are available. We'll use more static types. We can represent a multiple arity method, like a method that takes 1, 2, or 3 arguments with different entry points. That helps us optimize. It avoids boxing things in an argument array, and it fits better into the JVM. So I'll walk through an implementation here of the array bracket operator, the array reference operator in the C code, and then show you what it looks like in JRuby. It's very similar. So if you look at array.c in MRI, in JRuby, you'll see these define method calls, RB define method, and this takes a class that we're going to put the method on, a name to assign to it, and then a pointer to a function somewhere that represents the body of that method. Then we have RB array a reference here. Again, this is a multiple arity, a variable arity method. So it takes in an argument array and a count of arguments, and then has to branch based on how many arguments there are. We'll follow the one argument path here. So here is RB array aref1 receives one argument. The bulk of the logic here, you'll see in the middle this switch and this arithmetic sequence, begin, length, step. This is for all the cases where it's not a simple number. It's either an arithmetic sequence, or it's a range, or it's some other structure. We'll pass that off to another method. But what we're really interested in is the simple case here. If it's a fixed num argument, a numeric argument, we go into RB array entry to actually grab the array entry. RB array entry, simple enough, just calls into an internal version of that operation. Here's the internal version. We grab the length of the array, we grab a pointer to all the array contents, do some bounds checking on it, and then down at the bottom actually access the spot in memory, the pointer in memory, where the value is contained. So that's the C implementation. In JRuby, so I mentioned that we can do specific arity versions. So this is the method implementation for one argument. We don't need to check the argument count. We don't need to raise an error because we know if we get to here, we've already got one argument. There's no argument length checking. You can see both of the names that we assign are up here in our JRuby method annotation. So rather than having to enter in multiple bindings of it, we just put more names in here. And then eventually we determine that it's a fixed num, and we call into our entry method. The entry method takes that value, does some bounds checking on its own, eventually bottoms out in this ultimate element internal function. And that's where we actually access our array internally in the JVM and then give you the value back. We also have some specialized versions of these classes for more optimized cases. Ruby array one object is if it's an array that only has one value in it. And the main difference here is that there's not a second level of array in there. There's just a field. We grab it. It makes a more compact object. So when there's a small number of elements in an array, we'll try to optimize it down to one of these small sizes that's specialized for it. So how do you hunt down and find these core methods? Most of these classes are going to be in the org JRuby package. All of the methods that we bind to Ruby have this JRuby method annotation. So if you search for that, you can find them. We also try and include in our code some comments that say what the equivalent JRuby version is. So RB array new, if you search for it, it'll take you right to our new array functions in JRuby. And we'll talk a little bit more about that API in the last section here. This is kind of a good place where we can jump off into how we do native extensions. So of course we want to use pure Ruby as much as possible, but sometimes we need more performance or we need to call out to an external library. In JRuby, this is done with a C extension. On JRuby, we don't support the same C extension API, but we have essentially an equivalent API for JRuby, a Java extension API. Now, when you need an extension, there's three things that we would recommend you consider. First of all, if you can just use pure Ruby, that's usually fine. We optimize very well. Oftentimes, you don't need to drop down into Java code to get good performance out of that code on JRuby. But maybe it's a library you need to call. Well, if it's a JVM library, you can just call it from Ruby code. You can import the classes, call all the methods. It looks like you're just calling into another Ruby class. Similarly with FFI, you can pull in native libraries, use the foreign function interface, and call all those from Ruby code. But if you really have to, you can port the extension into our JRuby API. So couple quick notes on Java integration. Like I say, any library on the JVM written in Java, Kotlin, Scala, Clojure, whatever, can be pulled into a Ruby application and called from Ruby code without writing anything, without compiling any Java code or JVM bytecode. And we do a lot internally to optimize this, to make it work well. We also provide a bit of ecosystem help to pull in dependencies for libraries so that they can be bundled into a gem. The steps for calling JVM libraries: you require in the jar file, just like you would any other Ruby library. Java import a specific class into your local namespace. Create the object, call the functions. We provide both camel case and underscore case versions of everything, and some niceties like turning Java getters and setters into attributes. Lots more examples on the wiki I won't go into. Here is a quick little walkthrough example. So this is bringing up a JRuby IRB session. We are going to use the Java Swing GUI components here. First of all, we create a JFrame with the words JRuby is awesome. We create a button with it's going to tell you to push me, press me. We add the button to the frame. We set the size of the frame, 300 by 300, and then we show the frame. There we go. We have our GUI already done in an interactive session. Now we can bind some action listeners to it. So whenever the button is pressed, we want it to say, you pressed me, you push the button, and it calls the Ruby code and executes. And it's really that easy to call into JVM libraries. Definitely check out Glimmer. There's a workshop tomorrow which can let you use a lot of the same GUI libraries on JRuby without using any of the direct Java calls too. Yes. So I'm going to do a quick walk through the psych parser as an example of a C extension that's converted into Java. The psych parser has this while loop that basically iterates over all the parser events. It feeds the YAML into libyaml and pulls off events until they're done. So here we check if there's any errors during the parse, we get our position information, and then eventually drop down into this switch. This example is for if there's a YAML alias. We check if there's an anchor, create a string for it, and then RB protect down at the bottom ends up calling back out to Ruby, feeding those values out. Ours is very similar. Again, this was almost a line-by-line port. We're using snake YAML instead of libyaml. We get the next parser event, we get our position information, then we have our alias that checks if there is an anchor, turns it into a string, and again, does our call out to Ruby. So it's very similar. C extensions can be ported very easily, and we're trying to make that easier.
Yeah, however, we have a problem. Every Java method in our code base that's marked with public is basically our API right now. And we have to use public to call across packages internally. So we definitely don't want to expose every method we have. And so in order to prevent breaking native extensions, we basically will create a new method and the old method will just get deprecated. So we have over 1,500 deprecated methods in our core right now, and we need to fix this. So the plan is we're defining a new API package space so that no native extensions can go and update to it, like psych. And this API is going to be backported to 9.4, and we're actively using it in 10. So now once we get an extension to update to it, they just version lock to the latest version of 9.4, and then they're no longer our problem. So right now we have 3 classes with a bunch of static methods. We have create, which allows you to do things like new array, new symbol, new string. Error, which allows you to go and create the right Ruby exceptions that you want to throw, but it also has a nice formatting that you expect. Convert, which allows you to go and say, I have a Ruby object, but it needs to be a Ruby range. If you have a Java long, you can convert it into a Ruby fixed num. And here's just a quick example. There's two of these two. Oh, you did this different. Okay, never mind. So there's three methods that we're using. We're actually dog fooding this internally in our own code base. So the first thing that we call is cast as range. This makes sure that it's actually a Ruby range, and if not, it does a type error. Here's an argument error, which is a nicer syntax than what we had before. And then lastly, we need to get the begin and end for this clamp implementation and compare. So if we go over and look at Ruby range, you can see that we have these annotated as being a blessed API that we can use. So because we have these, the annotation in this API space will generate a nice guide. We're going to have an annotation that's going to allow people who are used to doing native C extensions to be able to say, well, what Java method should I call? And lastly, if you haven't contributed to JRuby and you'd like to, you can get involved in this. This is going to be the easiest way to get involved. It's just translating one method to another.
All right, so closing out here, how can you help and get involved in JRuby? We definitely need your help. Working on JRuby itself, there's complexity and there's challenges there, but the biggest way that you could help is just try out your applications, try out libraries. If you've got a library that you really depend on or that you like, make sure that the tests run in JRuby, make sure they're running in CI. If you find issues, file bugs. Anything that comes up, just file it. Maybe it's not our problem, we'll work through it with you and figure it out. Maybe you can help contribute by looking at the existing bugs and fixing them. We can write it in Ruby if you want to. We're fine taking in Ruby code. Doesn't have to be Java. We'll optimize if necessary later. I mentioned adding JRuby to popular libraries. Make sure that they have JRuby support. Make sure they're running us in CI. These are the things that we really need to stay fresh and part of the ecosystem. Join the community. We have a Matrix channel that we're on all the time. Matrix is an open source, open platform for doing Slack-like collaboration. That's where we've put our JRuby channel. There is also a Google group mailing list. Mostly just gets JRuby announcements, but there are occasional conversations there. You can also contact Tom and I directly. This is just what we do all the time, so please reach out to us. And there is some of our contact information and websites. We are going to be at the Hackfest tomorrow, so if you've got a library or application you want to try out, please stop by. Or if you'd like to get involved and help work on JRuby, you can do that too. So hopefully we'll see you tomorrow.
And I'd like to point out one other thing. This guy's looking for a job, so.
Yes, hire him. Hire him to work on JRuby. That would be great.
Yeah.
All right, thank you. I have time for one or two questions. Yes, you.
Are you really excited about anything coming from Leiden or Valhalla?
Yes, somebody who's been following this. So Leiden is a JVM OpenJDK project to reduce startup time, essentially. We're really excited because it's probably the biggest complaint we get about JRuby is startup time is just a little too slow. I've done some early experiments with it. It's looking very promising, and I'm working directly with the Leiden folks to help that out. Valhalla is bringing some features like value type stack allocation to the JVM. We will definitely take advantage of those to reduce some of our numeric object overhead. I removed some of the slides here for time, but we're also interested in Project Panama, which will make FFI native C calls very fast, already starting to use that, and Project Loom, which makes our Ruby fibers scale much higher, tens of thousands, hundreds of thousands of fibers. We're already using that, and you already get the advantage of if you pull down a new JVM. So we're tracking all of those OpenJDK projects. They all can help.
Well, thanks for coming today.
Yes, thank you.